Hi, so we're just going to spend a bit more time today looking at integration by substitution. So we did 4 examples in the last video using integration by substitution to integrate some functions that we could have integrated by inspection using the reverse chain rule. But as I mentioned in the last video, integration by substitution is something we need to be able to do, so it was a nice kind of gentle introduction. We're going to start off today by looking at this one. Okay. Now this is one, actually we can integrate by inspection, but there's a little trick to it that's not always immediately obvious. I'll talk about that once we've actually integrated it using substitution. So if we want to integrate this by substitution, we need to decide what our substitution's going to be if we're not already given it. Now the thing to look out for if we want to do in integration by substitution is we kind of look for an inner function, if you like. So because sec of 5x is being cubed here, I'm going to choose sec of 5x to use as my substitution. Okay, so I'm going to say that u is sec of 5x. Okay. Now I can already kind of hear some of you panicking, thinking we're going to have to differentiate sec there, and I can't remember what the derivative of sec is. Don't forget that if you look in your formula booklet, you will see the following. You'll see that if f of x is sec x, f dash of x, so the derivative, is sec x tan x. Okay, so this has just come from the formula booklet, so don't worry if you're panicking about what's the derivative of sec x. You are given it in your formula booklet, so in the exam you would have that result available to you. So now when we differentiate sec of 5x, we know we're going to get sec 5x tan 5x, and then we're having to use a little bit of the chain rule here. We need to multiply by the derivative of the inner function, so we're going to have 5 lots of sec 5x tan 5x. Okay, and the same as last time, what we want to do now is we want to rearrange this so that we make dx the subject. So I'm going to multiply through by dx and then divide through by all of that. So if we do that, what we end up with is that dx is 1 over 5 sec 5x tan 5x du. Okay. So we're now ready to make our substitutions, so we can make our easy substitutions just by replacing this sec 5x with u, and then we can replace our dx with all of that. Okay, so let's see what happens when we do that. So the sec of 5x cubed is just going to become u cubed, and then that's going to be multiplied by tan of 5x. No easy substitution to be made there initially, and then dx is going to be replaced by 1 over 5 sec 5x tan 5x du. Okay, so now same as last time, we look for things that cancel. Okay, and hopefully we can spot that the tan 5x's are going to cancel. Yippee, so things are starting to cancel down and nothing else so far. So what we'll do is we'll just tidy up, and we're going to have u cubed over 5 sec 5x du. Now at this point, things haven't cancelled down enough for me to integrate. I've got a function that I'm trying to integrate with respect to u, but I've still got this x lingering around. So what we're going to do is going to be something that we do a few times today, is we revisit our substitution. So if we go back up here now and look at our initial substitution, we can see that sec 5x is u. So I can now make that replacement again down here. So we're using the substitution for a second time. So if we do that, we end up with u cubed over 5u du. And then we do have a function that we are only trying to integrate with respect to u, which is only in terms of u. So tidying that up, I'm going to pull out a factor of a fifth, and then the u cubed over u is just u squared. Okay. So then integrating the u squared is just a third u cubed plus c. So overall we end up with a 15th of u cubed plus c. I was a little bit impolite to leave our answer in terms of u when the function we were asked to integrate was in terms of x. So we're now going to replace u with sec 5x. So we end up with a 15th sec 5x cubed plus c. Okay, and we're done and dusted. Now what I did say was we could have actually done this one by inspection. Now it is to do this one by inspection, there is a little bit of a trick to it. So this is just a bit of an aside. If we did want to integrate this one by inspection, we need to use a little trick. Now what I'm going to do is I'm going to write the tan 5x at the front, and then I'm going to write the sec 5x all cubed at the back here like this. Now if we look at that, that's not in the form k f dash of x f of x to the power of m, because the derivative of sec, as we know from our formula booklet, is sec tan. So to get this in the correct form, what we would have to do is we would have to write this as sec 5x tan 5x, and then in the brackets we'd have sec 5x squared, because I borrowed one of these sec 5x's to bring down to the front. And then once we've got it written like that, we can see that what we've got here, this bit is the f of x to the power of n, and then this bit here is the k f dash of x. So it's now written in that form where we could reverse the chain rule if we wanted. So you may well at this point decide that you're going to take this from there and try and use the methods we did the lesson before last in terms of using integration by inspection, reversing the chain rule, and seeing if using that method gets you to the same answer. Okay, so that'd be a nice way to spend a few moments. Okay, so hopefully that made sense. So let's have a look at another example. So today we're just focusing on integration by substitution. So here's our next one. So hopefully when we look at this one here, we've got the integral of 4x multiplied by 2x plus 1 to the power of 5. Hopefully we can see that this isn't in the form where we can integrate it by inspection. The reason being, we have got a function being raised to a power, but I haven't got a multiple of the derivative of this in a function here at the front. I've got a linear function here, so if it was in that form, I'd want a constant at the front, whereas I've still got a linear function there. So it's not in that correct form where I can use the reverse chain rule. Okay, so what we're going to do is we're going to try and use substitution. So what we said in the last one is when you're trying to choose a substitution to make, try and identify an inside function and use that as your substitution. Okay, so what I'm going to use my substitution is 2x plus 1. So I'm going to say that u is 2x plus 1. Okay, and as last time, what we do is we deal with the substitution before we do anything else. So we're going to have du dx is just 2. So then rearranging this, multiplying through by dx, dividing through by du, I'm going to get that dx is a half du. Okay, so let's go back to our function now and make some substitutions. So 4x at the front, not much to do there, can't make an easy substitution. The 2x plus 1, however, we can just replace with u. So we end up with u to the power of 5, and then the dx I can replace with a half du. Now we can tidy up a little bit. This half is going to partially cancel with that 4 just to give us 2. So we end up with 2x times by u to the power of 5 du. So we end up in a similar position to last time in that what we've got is we've got a function in terms of u and x that I'm trying to integrate with respect to u. Well, that's no good, that's not going to help. So what we need to do is we revisit our substitution. Now, I haven't got anything I can easily replace 2x with, but I'm going to go back to my initial statement, which is u equals 2x plus 1. And what I can do is I can rearrange this to make 2x the subject. So if I rearrange this, I'm going to get that 2x is u minus 1. So I can now use this here, this substitution, and say, well, I can replace 2x with u minus 1. So if we do that, we end up with u minus 1 multiplied by u to the 5 du. Okay, So hopefully we can see that this is a relatively straightforward integration now. We can just multiply that bracket through by u to the power of 5, which is going to give me u to the power of 6 minus u to the power of 5 du. And integrating term by term, I'm going to get a 7th u to the 7 minus a 6th u to the 6 plus c. It's a bit impolite to leave my answer in terms of u when my original function was in terms of x, so I'm now going to replace u with 2x plus 1 again. And we're done. Now, once you've seen this idea of using the substitution a second time, it's very tempting to just try and do it straight away, right from the get-go. I'd like to try and discourage you from doing that. The reason being that quite often, if you do that, it's not as obvious when things cancel. Only make the straightforward substitutions to start off with and see if things cancel first, okay? And then, and only when you've cancelled things down, return to the substitution for a second time if you need to. Okay, but it's worthwhile making the easy substitutions, seeing what cancels down, and then return to the substitution for a second time only if you need to. Okay. So let's have a look at another one. Okay, so this time, I just need to put that bracket there. This time we are actually given the substitution to use, but hopefully you might have spot that the substitution given slightly differently. Normally the substitution is given in the form u equals and then some basic function of x. In this case, actually, we've got x written in terms of u. Our approach is similar though. What we're going to do is we're going to differentiate. So this time, rather than having du dx, we're going to be differentiating x with respect to u. So we get dx du. And when I differentiate u squared with respect to u, I get 2u. Same as usual, we now rearrange this to make dx the subject. So we just get that dx is 2u du. Okay. So, once we're at this point, make some hopefully obvious substitutions. So we've got 1 in that denominator. Now, if x is u squared, the square root of x is just going to be u. So each root x is going to become u, so we end up with u lots of 2 plus u. And then in place of that dx, I'm going to have 2u du. So tidying up a little bit, we're going to have 2u over u 2 plus u du. And then because we've got a factor of u in the denominator and a factor of u in the numerator, we can cancel those down. So we end up with 2 over 2 plus u du. Now at this point we need to think about how do I integrate this function. It may be tempting to try and bring the denominator up. However, if you look carefully, hopefully we can spot that what we've got here is we've got something in the form where we've got a function in the denominator, and in the numerator I've got a multiple of the derivative. Okay, so it's in this form k f dash of x over f of x. So we know that when we integrate this, we're going to get a logarithm. So this is from the lesson before last. So when we integrate something of this form, we leave the numerator alone, and we put the denominator in the natural log function. And then we divide by the derivative of the inner function. Well, our inner function is 2 plus u. The derivative of that is just 1. So we're dividing by 1. We don't need to state it. And we have plus c. Same as usual. What we now need to do is we need to write our function in terms of x, seeing as our original function was in terms of x. So we're going to have 2 ln 2 plus, and u is going to be root x. And we're done. Okay. So one last example, a slightly unusual one. This is my favourite example of the day. So we've got a function here, and then if we look at our substitution, you are entitled to think, how on earth is that going to help us? But this is one of these nice situations in maths where something a little bit strange just seems to make things work beautifully. So let's see what happens when we try and integrate this function with x being sine theta. So we're going to differentiate. We've got x and our functions in terms of theta. So when we differentiate, it's going to be dx d theta. And hopefully we can remember that the derivative of sine theta is cosine theta. Okay. So rearranging that to make dx the subject, we then get dx is cos theta d theta. Okay. So returning to the function that we wish to integrate, we have 1 over, and then here we've got x, so x squared is just going to be sine theta squared. So we have 1 minus sine theta squared, and then in place of our dx we've got cos theta d theta. Not looking particularly nice. There's no obvious piece of cancelling, but at least it is all in terms of theta, so let's persevere. So that cos theta can go up in to the numerator. Again, no obvious cancelling, but hopefully we may spot that we can replace 1 minus sine squared theta with something else. If you think back to your the very first two trig identities you learned, you got that sine squared theta plus cos squared theta equals 1. So we can rearrange this and say that 1 minus sine squared theta equals cos squared theta. So we can see that what we've got down here I can replace with a cos squared theta. So if we do that, we're going to get cos theta over the square root of cos squared theta d theta. Now, the square root of cos squared theta is just cos theta. These are just going to cancel out. So we end up, after doing all of this, having to integrate 1. The integral of 1 with respect to theta is just theta plus c. Now, remember our function was in terms of x that we wish to integrate, so our answer should be in terms of x. So if we go back up here now, we can see that x is sine theta. So if we take inverse sine of both sides, we get that theta is inverse sine of x. So that means our final answer is going to be inverse sine of x plus c. And we're done. I think that's lovely, because what we've got is we've got an algebraic integral there. We brought in a trigonometric substitution, and we showed that this algebraic integral gives me a trigonometric answer, which I think is a little bit surprising, but hopefully you enjoyed that as much as I did. But I'm a maths teacher, so I'm strange. Right, those are the 4 examples I'm going to go through today. What I strongly recommend you do following that is from the textbook. So on page 207, these steps here, you might want to look at those, but we're going to use those more for when we do definite integrals, so integrals when we've got limits. It's worth having a look at this example here before you have a go at any questions, so hopefully you'll be able to follow this after the examples I've just been through. Then over the page on 208, for now, don't worry about this. This is what we're going to have a look at next week when we've got limits and we're using integration by substitution. But there are plenty of questions here at the bottom of page 208 for you to have a go at. Basically, questions 1, 2, and 3, everything there is would be a good idea, something that would be useful for you to have a go at. Question 4, don't touch. That's what we're going to have a look at next lesson. If you do want a bit of a challenge, you could have a look at some of the questions at the top of the next page. So question 5 looks fun. Question 6 looks fun, a bit of a factor theorem going on there, which looks exciting. 7 looks good, but there's a few there to have a go at. But anything with limits, leave for now, because that's what we're going to move on to next week. Okay, so hopefully that video was of use. and hopefully you feel confident enough to have a go at some of the start of exercise 11C on page 208. As ever, any issues, either message me through the VLE or send an email to my school email, and I'll do what I can to help. With this work, if you do come unstuck on any of the questions, it's really useful if you send me a photo of your work, because it might be that you're doing the right things and you're just making a small error that I'll be able to pinpoint for you. Okay, that's it then. Have fun with your integration by substitution.